This video illustrates three variations of a model of discounted cash flows over a 10-year period. Each variation indicates a possible way of modeling revenue growth through time. The basic model, the first variation, is shown here. There is an initial investment cost incurred right away at the end of year 0. Then at the end of every succeeding year, there is a revenue, a fixed cost, and a variable cost. The model assumptions are the following. The investment cost has a triangular distribution that is heavily skewed to the right. The year 1 revenue has a triangular distribution that is slightly skewed to the left. The annual fixed cost is the same every year, and this common value has a symmetric triangular distribution. The annual growth rate of revenue is the same percentage each year, and this common percentage has a normal distribution. Its large standard deviation implies that revenues could very well decrease every year. The annual variable cost is the same percentage of revenue each year, and this common percentage is normally distributed. These assumptions lead to the uncertain quantities in the green cells. Then the discounted cash flow calculations are straightforward. Note in particular how the revenue cells in row 16 use the same percentage change each year. The outputs include the NPV of the cash flow stream found with Excel's NPV function, and the internal rate of return found with Excel's IRR function. To illustrate a possible twist, there is also a bonus that is received if the NPV exceeds $50,000. In this case, the bonus is the NPV in excess of $50,000. Each of these three quantities has been designated as an at-risk output. Finally, several summary statistics are calculated to the right with at-risk statistical functions. Of course, these aren't relevant until the simulation is run. Note that the outputs shown here are based on the means of the uncertain quantities because at-risk's dice button is toggled to static. But if it is toggled to random, you can see how much the NPV varies. In fact, it can very easily become negative, in which case the IRR is undefined and returns an error. There's a case. This will be evident in at-risk's results, which indicate the number of iterations where an output cell returns an error. I will now run a simulation with 1,000 iterations. It is evident that the distribution of NPV is skewed to the right, with about a 44% chance of being negative. Also, the bonus is usually 0, with probability about 62%, but its distribution has a long tail to the right. Also, if you click the summary button for another view of the results, you see that the IRR cell contains an error in over 100 of the 1,000 iterations. This is again because the IRR can be undefined when the NPV is negative. The second variation, Model 2 shown here, allows the revenue growth rate to be different each year. Specifically, each year's growth rate has the same normal distribution as in Model 1, but each year's growth rate is an independent draw from this distribution. Therefore, there is a whole stream of green uncertain cells that are then linked to the revenue calculations in row 19. Otherwise, the model is exactly the same as before. The dice button is currently toggled to static, but if it is toggled to random, you can see how the growth rates can vary wildly from year to year. Again, I will run a simulation with 1,000 iterations. They indicate a much different distribution of NPV than in Model 1. In Model 1, if the single growth rate is highly positive, the revenues grow by this large rate every year. The same is true in the opposite direction if the single growth rate is negative, but the effect isn't as large because large negative values aren't as likely as large positive values. The overall effect in Model 1 is to pull up the mean, increase the standard deviation, and make the NPV distribution skewed to the right. But in Model 2, the good years tend to cancel the bad years, so the mean and standard deviation of NPV are both lower, and the distribution is more symmetric. Which is more realistic, Model 1 or Model 2? You could easily argue that neither is totally realistic. Model 1 assumes the same growth rate each year, which is unlikely to be the case. But Model 2 assumes that they are independent draws from the same distribution. This allows revenue to decrease by a lot in one year and then increase by a lot in the next year. This might allow more year-to-year variation than would ever be observed in the real world. The third variation, Model 3, is an attempt to correlate the revenue growth rates, although not as highly as in Model 1, which has perfectly correlated growth rates. It is arguably the most realistic of the three models. To model the correlation, a correlation matrix could be used, but this would require a 9x9 correlation matrix for the 9 growth rates. A simpler way to build in correlation is to assume that the growth rate in any year is the same as the growth rate in the previous year, except for an additive noise term. The noise in any year is assumed to be normally distributed with mean 0 and standard deviation 3%. Cell E16 contains the first growth rate from year 1 to year 2, which has the normal distribution that was used in the previous two models. Then each succeeding growth rate is the previous growth rate plus that year's noise. Actually, this is equivalent to assuming that the growth rate in any year is normally distributed, with mean equal to the actual growth rate from the previous year and standard deviation 3%. The rest of the model is exactly as before. Now I will run a simulation with 1,000 iterations. As expected, because of the correlation, the results for this model are more like those in Model 1. The distribution of NPV is again skewed heavily to the right, with a large standard deviation. Surprisingly, however, the mean NPV is now slightly larger than in Model 1, about 42,000 versus about 36,000.